Hello, and welcome to another episode of Mathmania. I am Junyu, and together with me, Bernice and Matthew will be walking you through this video. Unfortunately, they are not with me due to the current COVID-19 situation. In this video, we will be covering modulus functions and the surprising number of ways you can use them. Be it on your paper, in your everyday life, or simply to create art, modulus functions open up to many possibilities and enables you to have every opportunity to be creative. Let's get started.
You might be wondering now, what are modulus functions? Here's a quick example. The blue graph is y equals to x, and the red graph here is y equals to mod of x. Note how it overlaps the blue graph when x is more than 0, but becomes its reflection in the x-axis when x is less than 0, and reflection in the y-axis when y equals to 0. Modulus functions, also known as absolute value functions, are functions that output the absolute value or magnitude of a number or variable. The output will be positive, no matter what input has been given to the function. How are modulus functions represented? As simple as it seems, the modulus functions are represented by two vertical lines sandwiching an expression. So what does the modulus function do? It gives a positive output irrespective of the input. That means that even if I input a negative value, there will always be a positive value as the output for the function. This is an example. According to the statements seen in the slides, if the value of x is greater or equal to 0, then the modulus function takes the actual value. But if the value of x is less than 0, then the function changes sign and takes the positive value of the actual value. Please feel free to pause the video and take a moment to digest the information. Here are some examples to clarify. If x equals to 10, then modulus x remains as 10. However, if x equals to negative 5, modulus x becomes the magnitude of negative 5. Or simply put, 5. If x equals to 0, modulus x will be equals to 0 too. We are definitely getting the hang of modulus function. Let's move on to the next part. What exactly is the difference between f of modulus x and modulus of fx? First, this is how we obtain the graph of y equals to f of modulus x. For x more than or equals to 0, retain the portion of y equals to fx when fx is more than or equals to 0. For x less than 0, copy and reflect the portion of y equals to fx in the y-axis. Do note that the graph of y equals to f of modulus x is symmetrical about the y-axis. This is the original graph of y equals to x minus 7. What happens if we add a modulus to x, becoming y equals to modulus x minus 7? As you can see in this transformation, for f of modulus x, every x input placed into the function will produce the same result as its positive value. With the mirror, you can see that the graph is now symmetrical about the y-axis.
What about y equals to modulus fx? To obtain this graph, what you need to do is to keep the portion of y equals to fx that is above the axis. For the part of y equals to fx that is below the x-axis, reflect it in the x-axis. Now I know that might sound a bit weird and it's a bit hard to understand, so here's a graph to make it easier. In this example, we'll be comparing between y equals to x minus 7 and y equals to modulus x minus 7. Notice how every result of y after inputting x into the function will be converted into its positive value. With the mirror, you can see that any part of the graph below the x-axis is reflected upwards. Here's a quick summary of what we've just covered so far. It's quite impressive for just 2 lines around a bunch of numbers. Pause the video if you wish to read the differences in greater detail. Now we'll be moving on to solving problems in real life. You know, the thing that math is supposed to do? Yeah, that one. Let's start with the basics first. The question here tells us that modulus x equals to 4, and we have to find the possible values of 2x minus 1. Since we have modulus x equals to 4, x can either be equals to 4 or negative 4. So here are the possible values of 2x minus 1, and there's your answer. Now we're getting into actual real-life problems. Here's the first one. A drone is programmed to fly a distance of x meters, and the time taken to reach that distance can be estimated using a formula t equals to x cubed plus 2, where t is the time elapsed in seconds. However, the drone occasionally malfunctions and flies in the opposite direction, giving a negative displacement. Draw a table and include values of x, fx, and t to plot a suitable graph. Alright, so admittedly this isn't a great question since it involves having a bit of physics knowledge, but yeah, we're still gonna have to do it. So, since displacement can be negative, but we can't have a negative time or distance, we'll have to use modulus x to ensure that we get a positive result. Therefore, we'll be using y equals to f modulus x. So using the equation of y equals to f modulus x, where fx equals to x cubed plus 2, here we've got the table of values and drawn the graph in Desmos. So that's that. Alright, here's the last question we'll be doing for today. A fisherman is sitting in his boat and notices a reflection of the sun on the water. The sunlight reflects off the surface of the water at point 00 and passes through the point 315. If the stream pushes the boat 6 units to the left of the reflection, and the man's eye is 24 units high, does the reflected light enter the man's eye? So first things first, what we're going to do is solve for the gradient, which we can do just by subbing in the values of 315 and 00. That gives us a gradient of 5. From here, we can use substitution to obtain the equation of y equals to 5x. And since it reflects at 00, we get a graph of a modulus graph. And since it's modulus, we'll be using y equals to modulus 5x. Same as the last question, get a bunch of values and draw a graph, again in Desmos. And from the graph, we can determine that when x equals to negative 6, the y value will be 30. However, since the man's eye is at the point negative 624, the sunlight will not enter the man's eye. Alright, that's enough of that boring math stuff. Let's go for something that's more aesthetically pleasing. Junyi will now be showing us how, with the help of modulus functions, we can create interesting art.
Hello again, I'm back and I will now be showing you how the modulus functions can be used. This is a cutout scene from Pokemon Sword and Shield, showing Ash successfully catching a Pokemon. I'm sure that many of you have watched Pokemon before and know about the capsules used to catch them. That's right, it's the Pokeballs. This design which is being showcased is the most basic of all the multiple types that exist. Let's take a look. This is the Pokeball that is sketched out on Desmos using just graph and their modulus. It looks amazingly similar to the actual ball, right? The graphs are color coded using different colors to show which part of the Pokeball is made using which graph. Although this same design of the Pokeball can be made using circle equations too, what you are seeing currently is a more efficient way of using modulus functions to produce the same results. The first graph, outlined in black, is an example of y equals to mod of fx. As seen in the slides, let root 36 minus x squared to be fx. The graph is reflected about the x edges. Next, the graphs outlined in red are examples of y equals to f of mod x, where the graph is reflected in the y-axis to form the smaller circles. This shows that using either y equals to mod of fx or y equals to f of mod x will be fine when creating a circle. Lastly, for the graphs outlined in blue, you can see that both the y values and x values are modeled to form the 4 lines at once. From this application, we see how modulus function can help us be more efficient when graphing. This is the link to the Desmos graph. If you would like to fiddle around with the values or simply test it out yourself, you can go to the link as shown here. I hope that through this video, you have a clearer concept of modulus functions. Here are the different websites used in the making of this video. Thanks to these websites, we are able to create such a wonderful video. I hope you guys have learned something new from this video and are able to apply it in different contexts. If you like this video, make sure to give this video a thumbs up. And if you have not already subscribed to our channel, make sure to subscribe for more quality contents. Thank you, and we hope to see you in the next video.